Okay, thank you very much for giving me the opportunity to give this talk. My name is Mirko. I'm a postdoc at the Kavli Institute for Cosmology in Cambridge. And today I will present some of the first results from the KLEVER survey, a survey conducted with KMOS at High Z. Here you can see some of the people involved in the project. So the idea behind KLEVER is that despite the tremendous progress provided by near-infrared spectroscopic surveys in the last decade of high-redshift galaxies, which allowed us to characterize the properties of the ISM in galaxies at the cosmic noon in terms of chemical abundances, ionization and excitation mechanisms, gas density and pressure, dust extinction properties, and so on. Many of these surveys were affected by two main, I would say, problems. On one side, most of them were targeting only, was focusing only on one band usually and targeting only few emission line diagnostics, whereas on the other hand, most of the spectroscopic surveys in the last decade were basically long slit spectroscopic surveys, so they were totally missing the spatially resolved information of high-redshift galaxies. So to try to overcome at least partially these two problems, the KLEVER survey comes into play, and KLEVER is actually an ESO-large program which is now completed and which was aimed at observing 200 galaxies, around 200 galaxies between redshift 1.2 and 2.5 with the multi-object near-infrared IFU spectrographs KMOS on the DLT. The idea, as I said behind the survey, was to observe each of the target in the three main near-infrared bands, so namely Y, J, H, and K, in order to map the entire set of rest frame optical nebular diagnostics and move beyond a single slit or single diagnostic approach to get a full spatially resolved spectral information of the ISM properties in high-redshift galaxies. Here you can see an example of what we can get from our survey in terms of what we map for galaxies at redshift 1.3 from HB and oxygen 3 in the J band up to the sulfur 3 doublet in the K band, whereas for galaxies at redshift around 2.2, we map the oxygen 2 and the neon 3 in the J band up to the H alpha and nitrogen 2 and sulfur 2 in the K band. The sample is comprised of both lensed galaxies, lensed by foreground clusters in the frontier fields and clash clusters, and whereas half of the sample is comprised by galaxies, unlensed galaxies in the Candles fields. We have also included a small sample of strongly lensed galaxies which have been observed with Symphony in previous pilot programs. And overall, you can see in the bottom right panel the redshift, the spectroscopic redshift distribution of our survey. You can see that unlensed galaxies dominates the redshift range around 2, whereas lensed galaxies are predominant at redshifts around 1.4. This is the distribution of our galaxy sample in the stellar mass transformation rate plane. As you can see, I would just like to highlight how the fact that lensed galaxies allow us to probe the distribution in this plane down to stellar masses below 10 to the 10, which is something which is much more difficult for scene limited surveys of unlensed galaxies in general. Lensing magnifications allow us to go down to stellar masses around 10 to the 9 and even lower. In terms of how we deal with lensed galaxies, of course, to retrieve the full intrinsic properties of galaxies in the source plane, we implemented a set of customized models for strongly lensed galaxies observed with Symphony, whereas we exploited the publicly available models for the frontier field clusters for the galaxies observed with KMOS in the frontier fields. So the emission line fitting has been performed on the image plane, on the data cube, and then surface brightness maps have been reconstructed into the source plane, recovering a native resolution of around 2.5 to 3.5 kiloparsec, with typical magnifications ranging between 1.2 and 2.5. Of course, during the reconstruction process, the seeing limited KMOS PSF is affected, and it becomes basically more stretched and elongated into the source plane. And this has been taken into account when deriving, for example, metallicity gradients, as I will show in a few moments. So these are just two examples of what we can get in KLEVER when we have the full detection of all the emission lines. So for galaxies at redshift 2.2, around 2.2, we can map different emission line ratios, nitrogen 2 over H alpha, oxygen 3 over H beta, sulfur 2 over H alpha, and oxygen 3 over oxygen 2. Whereas for galaxies at redshift 1.4, we can map even the sulfur 3 over the sulfur 2 line ratio, which is an excellent proxy of the ionization parameter, for example. So combining all of these information together, it is possible, for example, to derive more robust estimates of metallicity in our galaxies and reconstruct 2D metallicity maps and derive and investigate the shape of metallicity gradients. So this is what we have done in our first paper, which has been published last year. Here I'm showing some example of the metallicity maps and gradient extracted from the first subsample of lensed galaxies which have been analyzed. Again, as I said, when extracting the metallicity gradients from the metallicity map as reconstructed in the source plane, we have taken into account the elongation of the PSF produced by the delensing modeling into the source plane. The main result here is that the vast majority of the galaxies we have analyzed so far are showing metallicity gradients which are fully consistent with a zero slope, so with being flat. But we have also found evidence of just a few inverted gradients, which means that gradients which have positive slope, in which the central region of the galaxy are less enriched than the outskirts, which have been interpreted as an evidence of accretion of pristine gas from the cosmic web at this redshift. If we try to investigate and visualize which is the evolution of the metallicity gradients with redshift, here I'm showing a collection of metallicity gradients, both from KLEVER, which are the viewpoints here in the plot, and from different surveys in the literature, both at high redshift and in the local universe. We can clearly see that on average, metallicity gradients between redshift 1.5 and 2.5 are consistent with a zero slope within the uncertainties, showing only a mild evolution with cosmic time. And this is basically in contrast with what is predicted by cosmological simulations and chemical evolution models, which are based on a pure standard inside-out mode of galaxy assembly, which would predict instead metallicity gradients which are much more negative at high redshift and then flattening over time towards the present day. So in order to reproduce the observed flat gradients, chemical evolution models need to implement enhanced feedback modes and account for radial flows and a redistribution of enriched gas in the ISM over large scales in these galaxies. Okay, this is a slide just to recap that now the survey is completed and the analysis of galaxies in the fields, in the Candles fields have been is terminated. So we now have full sample of metallicity gradients and nothing really changes in terms of the global pictures outlined before. These are just a few examples of more maps and metallicity gradients that we can get from our KLEVER survey. But before moving to the next topic, I would just like to stress that at this level, at the high redshift, sometimes radial gradients as extracted by actually azimutally averaging metallicity maps within circular or elliptical apertures in our case, due to the shape of the PSF into the source plane, may not be totally representative, totally informative in terms of how, and in terms of what is shown from the full 2D metallicity maps. Just as an example, I'm showing here three different galaxies here whose radial extracted gradients is fully consistent with a zero slope, but whose metallicity maps are totally different. So in some cases, flat metallicity gradients is really representative of an almost homogeneous distribution of metals throughout the galaxies, whereas in other cases, the metallicity maps is much more complex and irregular, and the flat gradient arises only by the fact that when you extract the metallicity in apertures, you're washing out non-axis symmetric features in the metallicity map. So of course, with KMOS and seeing limited observations, even in lens galaxies, we cannot really fully resolve most of the time irregular features in the 2D metallicity maps. But I think that with the JWST, which will go much more deep and will have a much more higher resolution, we would need to move beyond considering radial gradients as the only constraints for galaxy evolution models and simulations at high redshift. Okay, in the second part of the talk, I would like to focus a little bit on a different topic, which concerns the evolution of galaxies in the BPT diagnostic diagrams. And as Ryan already mentioned before, galaxies at high redshift have been observed to show an offset in their position on the typical nitrogen 2-based BPT diagram, for example, with respect to the tight sequence of galaxies observed in the local universe, for example, in the Sloan Digital Sky Survey. So photoionization models are capable of reproducing this offset by varying different input parameters, from the ionization parameter to the hardening of the incident radiation field to different chemical abundance patterns. But of course, they are affected by many degeneracies, and different observational constraints are needed to fully break the degeneracies in the models. So here I will present kind of a different approach in order to try to characterize the physical properties of galaxies in the BPT diagrams, starting from what we see in the local universe, for example, from the Sloan Digital Sky Survey. So if we focus initially on the N2 BPT, we know that the N2 BPT is in particular, the star-forming galaxies in the N2 BPT forms quite a tight and smooth sequence in the gas phase oxygen abundance, as you can see also here in the right panel. But the BPT is not only a sequence of oxygen abundance, of metallicity, but it can be shown that it is the position of star-forming galaxies along the sequence in the BPT is driven by different properties. Namely, the position in the BPT depends on stellar mass, on star formation rate, on for example, the velocity dissipation of the gas, on the electron density, on the ionization parameter as traced, for example, by the oxygen 3 over oxygen 2 line ratio. So the idea is that can we quantitatively assess how each of these properties contribute to the position of the galaxy and to the offset that we see of the galaxy with respect to the best fit of the local sequence of star-forming galaxies. So in this framework, as I said, if we consider the N2 BPT, for example, as in particular the star-forming sequence in the N2 BPT as a sequence of gas phase oxygen abundance, we can assume that a variation in oxygen abundance moves a galaxy along the sequence, but lines of constant O over H are actually perpendicular to the sequence itself. So oxygen abundance that moves the galaxy along the sequence, and a variation in different properties, which instead characterize the scatter and the offset perpendicular to the sequence itself. And we can indeed color code here, for example, each of the galaxy from the Sloan, each of the star-forming galaxies from the Sloan on the N2 BPT by means of the relative variation in different physical properties with respect to the average properties retained by galaxies which lie on the best fit local sequence. So the idea is that can we quantify how much of these parameters contribute to the observed scatter in the BPT? And to do so, we can try to solve two different kinds of problems. On one side, a simple classification problem try to predict whether galaxies lie above or below the best fit of the local sequence according to the deviation in each of these parameters considered here. Whereas on the other side, we can try to actually predict the exact level of offset, the exact level of the distance of a given galaxies from the best fit local sequence. And to do so, we have implemented machine learning algorithms, both artificial neural networks and random forest, to try to solve both these classification and regression problem. Now, without going into all the details of the networks, Artificial neural networks have been trained and tested on SDSS galaxies by feeding the network either with each of these individual parameters alone and with all the set of parameters together. So in terms of the classification task, we see that the network, when the network is fed with all the set of parameters together, it achieves an accuracy of more than 95% in predicting whether a galaxy is located above or below the best fit of the local sequence in the N2BPT. Whereas in terms of the analysis of individual parameters, we see that the deviation in N2 over O2, or nitrogen 2 over oxygen 2, which traces basically the deviations in the nitrogen over oxygen abundance, is perhaps unsurprisingly the parameters that performs better in terms of predicting whether the galaxies lie below or above the best fit local sequence. So, yeah, okay, thanks. Yep. Yeah. We did the same thing by training and testing, in this case, a random forest decision tree. The main advantage of the random forest with respect to the artificial neural network is that in the random forest, we consider the performance of each parameter relative to the rest of the set in a sort of a competitive environment. So random forest implicitly allows to assess the relative feature importance of each parameter with respect to the other ones. And in terms of the classification task, we can see that the deviation in nitrogen over oxygen retain most of the relative importance with respect to the other parameters. And interestingly, many of these parameters we can see here are showing a relative importance which has been suppressed with respect to the performance obtained with the neural networks, which implies that their individual predictive power, which have been shown in the neural network approach, followed basically by the correlation with other parameters, which is nicely exposed by the random forest analysis. The same thing has been done for the regression problem, both for the neural network and the random forest. I'm quickly skipping a couple of slides here, just to show that in the regression problem, again, both random forest and artificial neural networks are capable of predicting the exact distance from the star-forming sequence with a high accuracy. And again, deviation in nitrogen over oxygen abundance is the most informative parameter in terms of its predictivity of the distance from the local sequence. Here you can see the result from the random forest for the regression task. Then I don't know if I have time, otherwise I will skip this part, just to show that, of course, we can do the same thing for the S2BPT. And interestingly, even if the random forest, for example, which I'm showing here, is not achieving the same accuracy in the prediction of the distance from the local sequence as shown in the N2BPT, nonetheless is capable of reproducing nicely the observed distance. And interestingly, the relative importance of the parameters for the S2BPT, which describes the offset from the S2BPT, is different from what respect to the N2BPT, in that parameters which are most related to star formation rate and ionization properties, namely the deviation in star formation rate and the deviation in oxygen 3 over oxygen 2, which traces deviation in ionization parameter, are the most predictive in terms of describing the position of galaxies in the S2BPT. Of course, the same thing can be done by exploiting the full manga data set, which allow us to combine both global properties and spatially resolved properties on local scales. And of course, the same thing can be done, although with a much lower statistics, of course, in KLEVER, but nonetheless with full coverage of the involved parameters thanks to the broad wavelength coverage of the survey. Last slide, just to highlight that the future of this kind of studies is JWST and JWST and MOONS. And in particular, I would like to highlight the fact that we've been awarded, as Ryan said, a program in the cycle 1 for JWST NIRSpec, 40-hour on source with a single individual grating, to go down to a sensitivity of 10 to the minus 19 in flux, and to be able to detect in individual objects the metallicity sensitive auroral lines in high redshift galaxies in a robust way for the very first time for a significantly statistically significant sample of galaxies. And this will allow us to both test and recalibrate the strong line metallicity diagnostics by a direct auroral lines detection, and also assess the redshift evolution of the mass metallicity relation and the fundamental metallicity relation, as well as the general allowing us to break the degeneracy between different interpretation of how ISM properties evolve in high redshift galaxies. So I leave here my summary slides, and thank you very much for your attention.